Let's do a demonstration of training a neural network to do image recognition. This data set we're going to be using is called MNIST. NIST is the National Institute of Standards and Technology, and they collected a handwritten digits data set. And then people got to play with training a computer to recognize handwritten digits. I think it originally started for the post office, like understanding what the addresses people are writing on envelopes. So let's show an example of some of the images we're going to be using here. So, 5, a 0, a 4, a 1, a 9, and a 2. Each of these is a 28 by 28 block of pixels. So you can see some of the pixelation here. So let's go up and take this from the start. I got the code here from the official PyTorch examples. PyTorch is software package that does neural network stuff. And then I've made some modifications, but not a lot. It starts with importing the libraries we need, like PyTorch or Torch. And then we tell it what the structure we want for the neural network. We want some convolutions. So that's the conv2D. That's a two-dimensional convolution. Don't worry about dropout. Here's more convolutions. Here's a max pooling, for example. And then there's a soft max at the end, like I mentioned. Um, Next, we'll tell it how to train the neural network and keep track of the performance as training progresses, because I'm kind of curious to see how quickly it trains. So here we're just like setting up some memory that we'll be storing things in. Here we're actually computing the predictions and then telling it to optimize by adjusting the weights to get a better prediction for that image or that batch of images. And then this is all just outputting kind of our progress so far and recording it. And then this is to just evaluate the model on the test set. Here we're setting up some parameters like how big of a batch of images should we use all at once. Um, and what's our learning rate and our learning rate decay. Those are things that we would talk about in like a really upper level computer science or applied math class, like the one of them I teach. But don't worry about them for now. And then it's often good to take your data and kind of standardize it, and make its mean equal to 0 and its standard deviation equal to 1. That makes it easier for neural networks to work on it. So we're kind of calculating the mean and standard deviation to use here, and then using them here. Some prior code just had them hard coded, like someone computed them and then retyped the numbers, which is not really good practice. So here's where we actually tell it, hey, go do the training, and it outputs each of these. It was taking, I think, a few seconds per line of output here. So it took a few minutes to train just using a CPU. I mean, you can get a GPU this way, but I wanted to be kind to Google. So I was doing the training. And now that was all pretty much original code that I copied from somewhere. So now let's look at some of the new exploration I was doing. So we recorded what's called the loss, which is kind of like accuracy, but you want low loss instead of whereas you want high accuracy. So you can see as we do more and more training, the loss started out pretty high. Often neural network training starts with just random numbers for those multipliers. And then it gets, reasonably lower as we go along, but there's still kind of some randomness depending on which images we're in, which batch of processing. Um, just out of curiosity, I decided to change the learning rate and make it slower, basically, and then retrain it. And then we'll see how now the loss doesn't decrease as quickly and doesn't get as low as it did in the other plot. Um, so in this class, we probably won't be worrying about it, but it is something that some people think about when they're training neural networks. Let's make a confusion matrix for the model. So here's our confusion matrix, and this is on the test data set. So Let's read this carefully. On the rows on the left here, we have the true label. So this top row is for images that were truly a zero in the data set. And then each column is what the neural network said, what it like its top one, what is the most likely thing for this digit. And so of the true zeros, 962 of them got labeled as a zero by our neural network. That's pretty good. Of the true ones, 1,000 some got labeled as a one by our neural network. So that's even better than the zeros. And we could start asking, like, what other digit was like most common among the ones? And we see the largest value in this row is here in the second to last column, which is an 8. So it wasn't doing it super often, but it was the most commonly confused thing for when there really was a 1, our neural network said it was an 8. Um, when it really was a 2, our neural network said that it was a 7 or an 8 20 times, 29 times out of roughly 1,000. Um, so that's a way to look at a confusion matrix and say, when it's really this, what is the most common mistake that it's making? That's a good question to ask. When it really was a 7, a 2 was the most common confused thing, and a 1 also somewhat common. We could also say, what was the per class accuracy? And we're computing that here. We've got this table. So on the training data, the per class accuracy was like 97%, 97%, 89% for a 0, a 1, a 2, or 3, etc. And then the test accuracy was, pretty much the same there. Um, we usually expect a little bit lower test accuracy than training accuracy, but here it doesn't seem like there's a huge pattern, and sometimes test accuracy is actually a little higher, but that can happen randomly. This is on the slower learning rates, so it didn't do quite as well as it could have on the faster learning rate. I was using AI to generate a lot of this code, as you might expect, and it also summarized the results for me, and it made this little table that doesn't come directly from the computer output, uh, but this is on the faster learning rate, and you can see the higher accuracy numbers. But what I want to point out here is the danger that the AI ran the code, or, wrote the code, had Python run it, took the output and put it into a text cell here, and then that doesn't update if I change how my learning rate goes or something. So you just have to be careful when you're letting AI do summaries for you. Remember that it won't auto-update those summaries. It's up to you to update them if you change something. Um, and again, here's those sample digits. Now we might ask, what if we gave it these digits that where the background is black and the digit itself is white? What if we tested it on something that was the opposite, what's called the photographic negative? So we still trained it on the black background, but then we're giving it white background and black digits. And let's take a look at its per class accuracy here. It's basically 0 except for twos. It got twos pretty okay, kind of funny. So that's a lesson that, oh, and here's the confusion matrix. You can see pretty much every digit, like truly fours, it labeled almost all of them two. Truly sixes, it labeled almost all of them two. So maybe half of them three. So it really did not do well, trained on one type of image and then tested on the photographic negative. Um, let's take a look at some other interesting things we could try. What if we train it at one zoom level and then run the AI on images from a different zoom level? So here I've taken those 28 by 28 original images, scaled them up to twice the size, 56 by 56, and smoothed them a little bit. So we trained it on these 56 by 56 images and then tested it on the original images just padded around the edges. So you can see these look a little blocky because they're the 28 by 28 digits, pixel digits. And how do you think that would go? Well, here's the confusion matrix on the test data. And, we hope to see a fairly large diagonal. It's kind of large, but not great. It did pretty well on the number 1, I guess. But it labeled a lot of things as the digit 9 when they weren't really the digit 9. So that's kind of disappointing. But not surprising. We can see how the per class accuracy goes. So some of them it was just really bad on, like 1% accuracy on the digit zero, for example. What if we tried to feed a 28 by 28 pixel image into a network that was trained on 56 by 56 pixel images? I tried that, just kind of the simplest possible approach, and I got some error message from Python, which is pretty much what I expected. Um, there's a variety of ways to handle that problem of I trained it on images this size, but now want to run it on smaller or larger images, and we can talk about those if you're interested. We might also try training on images where the thing of interest is in one part of the image usually, but then what if we want to test it on images where the main thing is somewhere else? So here I've got I trained it on images where the digit is always in the lower left corner. And then I'm going to test it on images where the digit is always in the upper right corner. Do you think it'll do a good job? Well, here's the confusion matrix we got after making predictions on that test set. And it basically thought everything was a one. So it did not do a good job at all. The per test accuracy looks pretty terrible, except for the number one. It predicted that really well. That's why we need that variety in our image database when we're going to train an image, or there might be some other techniques we can do to make it know to look in various places, not just in the center or in the lower left or something. This brings up the fact that there are some people have investigated, are there ways to fool AI that are possibly invisible to humans? So I'm mentioning this not because I think that you as a STEM person are at a high risk of someone deliberately messing up your images of yeast cells or animals or whatever, but it points out how CNNs still have kind of a lot of mystery to them. It's good to completely understand the tools that we're using when we can, and we don't entirely understand what CNNs are doing a lot of the time. So here's an example from a paper explaining and harnessing adversarial examples, where they take an image of a panda and the neural network is 57% confident that it's a panda. And then we add a very small amount of noise, like 0.00 something times this apparently random grid of noise. It's not quite random, but it sure looks like it to us. But then once you do that and rerun the neural network, then it's 99% confident that it's a gibbon, which is a kind of monkey or ape or something. But to our human eyes, this new picture doesn't look any different than the original picture because we're adding a very small amount of noise. Another example from a paper called Learning Securely is something that's a school bus, and then a very small amount of noise. The new image still looks basically like a school bus to us, but the neural network thinks it's an ostrich. And the same thing starting with this dog, adding a little bit of noise, we can convince the neural network that it's an ostrich. Um, People have also experimented with making visible changes to real world things before taking a photo, like convincing the AI that this is no longer a stop sign, even though humans would still say it's a stop sign, but it has a sticker on it or something. So just good to keep in mind that CNNs still operate in ways that we're still trying to figure out.